Alright, so this is Griffiths Electrodynamics problem 3.21. We are looking at a conducting sphere placed in a uniform electric field. So out at infinity we get a uniform field, and then and that's in, well, I guess everywhere out at infinity the field is uniform, but here at the sphere it gets distorted nearby the sphere, and so the potential is just going to linearly I guess decrease as we move here in the z direction. This is the z direction. Once we're out far away from the sphere, but close to this sphere, the potential is more complicated. We've got these free charges moving around and all kinds of stuff going on. So, going to the problem, what we're doing now is we are adding a charge to this sphere. So before this was electrically neutral. I believe there's we've done a video of a charge of a sphere in an electric field. You can also find it in Griffiths. This is example 3.8. All right. To save time, what I'm going to do is just give the result of example 3.8, but there's also a video of a conducting sphere in this field where we would solve for this. So the answer, which is, by answer we mean the solution for the potential outside of this conducting sphere, the answer is given by equation 3.76, which is given as a function of r, the distance from this center point right here, and theta, which is, if I were to draw this out to some point out here, this would be little r, this distance all the way from the center out to this point, and theta would be the angle with respect to this z-axis, or passing through the origin here. So again, the solution after this huge mess of using boundary conditions and Legendre polynomials and everything, the answer is equal to minus E naught. Okay, that's the strength of the electric field far away from the sphere. We have an r minus big R cubed over little r squared, and this is multiplied by a cosine of theta. Big R, by the way, of course, is the radius of this sphere. Alright, so now we're looking at, suppose rather than a neutral sphere, suppose we add a charge, big Q, onto it. Then what is the solution for the potential outside the sphere? And mind that we have to be very careful with where we're setting the 0 point. So in the case of just this conducting sphere that's neutral, we set the 0 point anywhere along this xy plane passing through this origin. Alright, again, this is the neutral sphere case. Alright, now this is just a basic, as usual we take more time than we need to take on these videos. This is a basic superposition problem. So in order to get a charged sphere, basically because of spherical symmetry, the potential outside the sphere will be just as if there were a potential, if we were to take a sphere by itself, just by itself, right, we're looking at superposition, right? So we have this case of a neutral sphere with potential given by this. Now we're looking at the other case for our superposition, which is just a charged conducting sphere with charge big Q. All right, so the potential out here for a charged sphere due to symmetry will look as if there is just a point charge of charge big Q at the origin. You can get this by Gauss's law and symmetry and all of that. So the potential for this case does not depend on theta, it only depends on r, and it is just the potential for a point charge Q at the origin. So 1 over 4 pi epsilon naught, we have big Q for our charge upstairs, and we have a little r for our distance from the origin. So this is the potential for this case, and this is the potential for the case of our neutral conducting sphere. For the superposition of these two, if we want the potential for a charged conducting sphere in a uniform electric field, we just add the two potentials together. All right. Our answer is just the sum of these two potentials. So 1 over 4 pi epsilon naught, big Q over r, and then we add on this potential minus E naught, we have a little r minus big R cubed over little r squared, multiplied by cosine of theta, where again this theta is this angle right here with respect to z. All right, so like Griffiths says, we just have to be careful with our where are we setting 0. So before, we set 0 along this entire xy plane. That's for this case. For this case, 0 is set out at infinity. And just with anything, so suppose we had two functions, right, and we're adding them together. Say here's a function f and here's a function g, right? We're adding them together. This maybe not a good, I didn't draw these very well, but you know, we can add these two functions and get some other function. The only ways for the sum of these two functions to equal 0 is if they happen to be equal and opposite, so they cancel each other out, or if they both happen to equal 0, which maybe they're equal and opposite if they both equal 0, right? I don't know. All right, so if they both equal 0, then we get 0, or if they're equal and opposite, we get 0. For this case, we could have both. So as we look at the potential here in the neighborhood of the sphere, there are places where we could have equal and opposite potentials from these two, and we would get 0 somewhere in the location of the sphere. That would be very complicated to calculate, most likely. Maybe not, you could try it. I'm not going to. The surefire way to find where, if I can just find one point, right, even just one point where the potential is equal to 0, just to use as a reference point, surefire way to find that is if we can find a place where both of these equal 0. And the place where that happens is out at infinity for this guy, so he's happy, and along this xy plane for this guy, so he's happy. They both equal 0 out at infinity along the xy plane. So if you picture like a ring of points in space in the xy plane, and then you expand that ring out to infinity, that's where our potential is equal to 0. That's not the only place where it's equal to 0. Like I said, if we have, or it's not necessarily the only place where it's equal to 0. If we had, again, places where the potential is equal and opposite in here near the sphere, then all of those points for the potential are going to be connected, right? We can't have any, you can't have like a region where the field is equal to, anyway, pretty sure, right, using Laplace's equation, you can't have like a local maximum or a local minimum. Things just have to be the average of their neighbors. You know, maybe you could get some weird complex saddle point or something, but because you can't have a local maximum or a local minimum, you can't just have like a nice little region where the potential is just 0 without any sort of boundary condition being set. So anyway, so it not only equals 0 way out at infinity on this xy plane, but there's also probably some surface that kind of curves in here somewhere, at where it is also equal to 0.